Now let's turn our attention to phases. First of all, let's define what we mean by a phase. It's a macroscopically homogeneous region in which all intensive variables vary continuously. And a phase transition is the transfer of matter across a phase boundary, across the interface between these phases. We're going to concentrate on first order phase transitions. In a first order phase transition, you have discontinuous changes in enthalpy and molar volume. For instance, when water is chilled, its density goes down and the liquid phase reaches a minimum at about 4 degrees C. And when water finally freezes anonymously, boom, the density actually decreases, right? The molar volume increases in the solid phase. Ice cubes float, right? Their density is less than that of water. But you can see how there's a discontinuous change between the molar volume of the liquid and the molar volume of the solid. That's a first order phase transition. Now, there are second order phase transitions in which the change is not discontinuous, which is continuous. An example of that is the liquid to glass transition. We're not going to talk about those right now, but it's an important type of transition, especially in polymers and other materials. So let's ask the question, what determines the relative phase stability? And to answer that, we're going to have to introduce the idea of phase diagrams. The first one we're going to look at is a chemical potential versus temperature phase diagram. Now we know how the chemical potential is defined, right? It's just the molar Gibbs energy of a pure substance. And we know how the chemical potential changes with respect to changes in temperature and pressure, right? The partial, how chemical potential changes with respect to temperature when we keep pressure constant is equal to minus the molar entropy. How the chemical potential changes when we change pressure is related to the molar volume. Oh, okay. So at equilibrium, we know the chemical potential of a substance is the same throughout, and that's true even if we have multiple phases. A system also evolves toward equilibrium, at which point its chemical potential is a minimum. So let's keep those ideas in our mind. And let's concentrate on how the chemical potential changes as a function of temperature, right? Minus S. The molar entropy is always a positive number, so minus Sm is always a negative number. Moreover, we know that the molar entropy of a solid is less than the molar entropy of a liquid at the same temperature, and the molar entropy of a gas is by far the biggest of all of these phases. Therefore, if we plot chemical potential versus temperature, we'll get one curve for a solid, one curve for a liquid, one curve for the gas phase. And we know that the solid has the smallest slope, the liquid has a bigger slope, and by far the greatest slope is that of the gas. Okay? So let's start out at 0 Kelvin. We're going to heat up our solid, and we'll see a decrease in the chemical potential that changes with a slope given by the minus the molar entropy until we get to a point where the liquid curve intersects the solid curve. This is where the melting point occurs. This is where the liquid and solid have the same chemical potential and they can coexist at that one temperature in equilibrium right there. But as we increase the temperature even further, the system has to switch over to the liquid chemical potential curve, and then it will continue to decrease at a somewhat greater slope now because the molar entropy of the liquid is greater than that of the solid, so we have a greater slope here until, boom, we get intersected by the gas phase curve. This is a normal chemical potential versus temperature phase diagram where the boiling point is higher than the melting point, right? At the boiling point, the gas phase and the liquid phase have the same chemical potential. They can coexist with each other. That's where you start to boil the sample. And as you increase the temperature yet further, at higher temperatures, you have to switch on to the gas phase curve. So now we know why these phase transitions occur. They occur when the chemical potential versus temperature curves intersect each other. Now, chemical potential is also a function of pressure, and we know how to write the chemical potential of an ideal gas in terms of the pressure, and it depends very strongly on pressure. Whereas in an incompressible liquid, or similarly for an incompressible solid, we only get a linear dependence, right? We get an exponential dependence for the gas phase. We get an linear dependence for the condensed phases. And if we plot those on the same set of axes, what we see is that the gas phase is much more sensitively dependent. Its chemical potential is much more sensitively dependent on the pressure than either of the condensed phases. Oh, that's very interesting, because that means this curve here, the chemical potential of the gas phase as a function of temperature, we can move this curve around quite a lot by changing the pressure. Indeed, for some compounds, you can move this curve so much as a function of pressure, right, that you can get it to cross the solid phase before the liquid. CO2 is an example of this, right? You know dry ice. Dry ice sublimates. It doesn't form liquid CO2 at atmospheric pressure. And the reason for that is that the gas for CO2, the gas phase chemical potential curve intersects the solid before the liquid does. When that occurs, we'll get sublimation before melting.